Okay, so I am going to start with PINTK because it is a very useful tool to explain one of the fundamental tools that the algorithm uses, actually. So, there we go. So, PINTK is a GUI, an interactive GUI, which is a graphical user interface that allows a person to time a pulsar interactively rather than having to adjust the model, pull up the residuals, look at that, compare it to the last fit, go in the par file and change the parameters. That instead of that involved process, you have this very nice GUI where in the upper left you have all of the different parameters that you can add to a model, position and the spin and spin down rate being the most important. In the lower left, you have these different color modes that can show you the different frequencies that an observation were made at, which, as an explanation, this data is simulated data. But for the algorithm, we had to simulate pulsars because there were just not enough actual isolated pulsars for us to test on, so we made our own. So this is simulated data, which is why the pulsar is called Fake 1, a pulsar I'm sure you've all heard of. And so along with the different color modes, you can also plot different axes, such as, the frequency, the errors, things like that. Those are unfortunately constant because this is simulated data and those are all constant for this data. So the way you would go through fitting a pulsar in this situation would be, you would say, where is the densest set of TOAs? Let's start looking at those so we can zoom in. An important note for PINTK is that zooming does also select the points that you zoom in on, and you unselect by hitting U, so that to select points you will probably have to unselect and reselect several times as you zoom in and look at your data. We can choose the first set of TOAs here since they appear to be in a line pretty clearly. We have F0, the spin rate, turned on, and we can tell it to fit. And as you will see, the points become very close to each other. And if we zoom out, we will be able to see that several of the points are now in a line as well. Here, I'm just going to reset the pane and zoom back in. So now these points, this was the set of points that we fit, and we are able to see that those are in a line now. So we can probably include more in the fit, continuing to just fit for the spin rate. And as expected, it fits a little better. And so, you would continue going through this process. But something interesting that PINTK can do is you say, oh, okay, these are in a line. What if I just decide to choose all of these points and I'm going to fit it for position? It'll be able to figure it out. So let me just, fit this, see what it looks like. This doesn't look great. That point's way out of alignment. Nothing else looks good. Maybe if I fit, a lot more data, would that work? Fitting for all these parameters? Probably not. No, it looks even worse. So what you can do is go down to the bottom and there's this revert button, which is basically an undo. So you can just revert back to that fit and then to the one before. And now we are back to the last point at which we were able to see that we had a good fit. We are only fitting for, we would have to turn the position back off. But now we've only fit these points. So that's a very useful tool to be able to say, I've made a mistake. I'm going to go back a few steps and start fitting from there again. So that is a lot of what PINTK as a GUI can do. Another thing that it can do that is very useful and relevant for the algorithm is we can say in the situation that we're in our point in the fit, that we have fit these several data points, the ones highlighted in yellow. We have fit those, we have a model with F naught. The decision we need to make then is that those blue points we want to include in the fit, and we're pretty sure, you know, the next 3 points we could pretty clearly see would be able to be included in the fit. But this one out here, you know, we're not exactly sure would that be able to be included in the fit. And the way you could decide that is just attempting to fit that to see if it works. But there is actually a way to make a good guess of whether you could include those points in the fit successfully using just the information we have now. And the way you can do that is that what we have currently in our model is the parameters, and for each parameter we have their best fit value and we have the error associated with them. And for each parameter you can say, if you have a best fit value and an error, you can create a Gaussian distribution for that parameter where the mean of the distribution is the best fit value and the error of the distribution, or the error of the parameter, becomes the standard deviation. And that creates a Gaussian distribution. What you can then do is start randomly choosing values from that distribution and create a new model. And what would that model look like? It would agree very strongly with the current best fit model at the points that you've already fit, but it would probably vary beyond those points. And if you go up here and click random models, and if I redo the fit, I will include right ascension now. It now shows these black lines, which, well, I'll let it go through a fit again, is exactly what I just described. So what these gray lines are is the program is looking at the covariance matrix of the current fit, creating a multivariate Gaussian distribution, choosing new parameters from that distribution, and then plotting those new models. And what you can see based on that is that there's, you know, I mean, there's a lot of information here. You can see that given the spread of these lines, that the next few data points are very clearly can be accounted, their difference from the best fit model can very clearly be accounted for by just varying F naught and right ascension. We don't need any new parameters. And we even got lucky. One of these lines goes almost exactly through the next 3 data points, and it is very likely that that model that it is projecting will be the new best fit model once we fit again. So these random models, or predictive models, because they help you predict what model to try next, are what the Algorithmic Pulsar Timer app is based on. But before I get to that, I will continue with random models on, go through the rest of the process of fitting this pulsar in PINTK. So we would select these points, fit them, let it recalculate the fit. And again, we can just zoom in now and we can see the spread of these random models shows that the next few points to be fit are very likely to be accounted for by the variation of the model that we already have. Zoom back out. And now we can see something else interesting, that the next point that we want to fit isn't in line with the predictive models. What that likely means is a new parameter needs to be included. I'm going to go ahead and make a guess and say that it is declination that needs to be included, and I can try that fit and see what the random models show. And that was exactly right. So now those points are all in a line. And if we move to the right, we can see that the next several points are also accounted for by the spread of these random models. And I'm going to guess, yep, we zoom all the way out and we can see that we have almost entirely phase connected the model. And if we include some more points and add in spin down, I'll fit again and then reset the pane. And we now basically have a final solution where the random models, as you can see, are still varying at the outside. If I fit it again, it will fit all of the data points at once. And so using those random models or predictive models, they can really help you in this interactive timing figure out what to do next, and they can just give you a lot more information. And PINTK as a whole is a very useful way to time pulsars interactively, because you can, undo and redo. It's very easy to make decisions, try things out, and go through timing like that. So that is a quick overview of PINTK. And now I'm going to move to APT, which stands for the Algorithmic Pulsar Timer. So APT is a program that is based very heavily on those predictive models that I just showed. So, and also, to keep myself on a time limit, I am only going to give myself until the end of the program, the algorithm solving this pulsar, which the same pulsar I can reset. This is the starting data that the algorithm is starting with. It is the exact same data that we started with when we started fitting it in PINTK. And I'm going to start running it, and we'll hopefully finish my explanation by the end of the time it is running. So APT goes through the same loop that we went through as people. We had a subset of TOAs and we had a model, and we had fit the model on those TOAs, and then we had new TOAs that we wanted to include in that model. The decision that we were able to make as humans is that we were able to look and see if there were any trends in the data, or we were able to try adding new parameters, but the algorithm needs a way to quantify that. And the way it does that is using these predictive models. So what it does is, with a subset of TOAs and with the model it has fit on those TOAs, it then calculates the predictive models and looks at the next TOA to be added. And it looks at which of those random models is closest to intercepting that next set of TOAs. It then chooses that as a new best fit model. And then this needs to decide whether new parameters need to be added. The way it does that is by calculating an f-test for each individual parameter. An f-test tells you the likelihood that the improvement of the model is due to actual statistical improvement rather than just randomly, you add another parameter, therefore it can always fit better. So it performs an f-test for each parameter. It decides if any new parameters need to be added at that point. Then now it has this new model that may or may not have new parameters. It fits the model on the entire set of TOAs with the fit TOAs plus that new set of data that you wanted to include in your fit. It does that, and it then looks for the next closest TOA, restarts the loop, and just continues with that process with expanding the model and the set of TOAs using the predictive models over and over and over again until it reaches the end of the data. I timed that very well. All right. So as you can see, this is the output of the Algorithmic Pulsar Timer. If you remember, it is the exact same solution that we came to when we solved it ourselves. You probably would like to see that the algorithm has truly solved it. I didn't just tell it to pull up a plot after 2 minutes. The way that we can do that, if I tell this figure to go away, is that while it doesn't have a reversion, it does not have a reversion feature in the algorithm. It does save an image and a par and tim file for each step of the process, and it also saves an array as a CSV file, as just a table that tells you which data points in the set it was fitting on at that point, which means you can re-enter the process of fitting the data at any point in the process and give it new input parameters and further customize it. So if we look at these images, we can see the algorithm going through, using the random models, making decisions, adding new parameters, and going through until it has fully solved the system and come to the same conclusion that we did.